All right, so we're going to look at solving quadratic equations over the complex numbers now. So some of the prior knowledge for this would be Introduction to Complex Numbers, which we spoke about in lecture 30, and just some solid foundations in understanding complex numbers, so things like the modulus, conjugate, and division. And obviously, given the nature of this topic, quadratics is obviously going to be very important. Just understanding quadratics really well in sort of real number space will be very helpful for this. And just some basics of 3D geometry, just for something that we're going to do at the end. So some of the key concepts we'll cover in this video will be factorizing complex quadratics. So move aside the difference of perfect squares. Now we're going to look at the sum of two squares. So we'll look at also completing the square, factorizing, and then we'll look at what's called the complex quadratic formula. And then we're going to look at visualizing solutions to complex quadratics, which I think is the most interesting part of this. So let's jump into it. If we're to look at factorizing quadratic equations over the complex numbers, one thing we can say, hopefully you're aware in sort of regular quadratic land with real numbers, that if you've got something like x squared minus 9, then that factorizes to x minus 3 multiplied by x plus 3. But we know in complex land that I squared is negative 1. So we can rewrite a sum of two squares as a difference of two squares. So for example, if you have z squared plus a squared, since I squared is negative 1, we would get z squared minus ai squared. And remember, that plus has become a minus because I squared is negative 1. So you'd have a negative here. And I squared is negative. So these two are equivalent. I think you would agree. So you can then factorize it as a difference of perfect squares. So it becomes z plus ai multiplied by z minus ai, just like you're used to, hopefully. Okay, so just a simple example here, z squared plus 3. If you factorize that, you're going to express it as z squared minus negative 3. Yep, because we sort of just factor in the negative here, so it's take away negative 3. So that's the same thing as z squared minus the square root of 3i squared. Remember, I squared is negative 1. So we put that, that would become positive there. So you get z minus the square root of 3i multiplied by z plus the square root of 3i. All right, let's look at solving quadratic equations over complex numbers again, but this time we're factorizing quadratic trinomials. So similarly to real number land, when you're factorizing a quadratic trinomial, you can complete the square. And I'll put some links below if you're not sure about that. But if you had something like some complex quadratic, q of z equals z squared minus 2z plus 5, then by completing the square, we get this thing. Remember, to get this value here, we half the b value, or the middle value, and square it. Half of negative 2 is negative 1, squared is positive 1. And then remember, we can't just randomly add a positive 1, so we take away 1, and we have to include the plus 5 there as well. So we end up with this, plus 5 minus 1 is positive 4, and then we factorize it just like before, using the sum of two squares in complex land. So it's z minus 1 squared minus 2i squared. Remember, I squared is negative 1. So all of this is positive 4, just written using the imaginary unit. And then that simplifies to this, z minus 1 plus 2i, z minus 1 minus 2i, when you factorize it using the difference of perfect squares there. So that is how you factorize complex quadratics. I suppose what I'll point out is this could be very useful for solving complex quadratics, which is what we're going to look at next. So let's have a look at that. So just like again in regular number land, real number land I should say, if you have some quadratic, in this case being complex now, so q of z equals az squared plus bz plus c equals 0, then the solutions are given by the quadratic formula. And again, I'll put some links below to explain exactly where the quadratic formula comes from, but now just notice that the left-hand side is now a complex number, z, rather than a real number, x, like it was before. So yeah, I think that's interesting in itself. But yeah, this is the exact same quadratic formula otherwise. And then so if we just look at an example here, we've got 2z squared minus z plus 1 equals 0. So a is 2, b is -1, and c is +1. And then whack that all into the quadratic formula. You'll notice that now that this part's negative, because we're in complex number land, we don't have to worry about having negative square roots, because you'll notice here we'll get 1 plus or minus the square root of -7, but that's just plus or minus the square root of 7i, because we can include that imaginary unit now. If that step's a bit confusing in terms of why the square root of -7 is the same thing as the square root of 7i, then definitely go back and sort of look at the introduction to complex numbers. But you'll notice we end up with this as our answer. Okay, what I wanted to step to now was explaining this in a bit more detail. I always like to have sort of a visual picture of what's going on, and it took me a while to wrap my head around visually how we could represent these solutions. And the reason I wanted that is because in two-dimensional space with real quadratics, the x-intercepts represent the solutions to the quadratic. But then in complex number land, it's a little bit more tricky. The question is, how do we sort of visualize that? So sort of bear with me here as we step through this. It's going to look complicated, but hopefully make some sense of it. So let's take some complex quadratic f of z, and it's the same as this one, 2z squared minus z plus 1. All right, but we know that z is a complex number now, okay? So wherever we see z, we're going to put x plus yi, because remember, the complex number is made up of a real part and an imaginary part. So x is the real part, y is the imaginary part. And so yeah, we put that in there for z, and then we put that in there for z here, and then we add 1. So we've written it sort of in expanded form, if we like, because we know z is equal to x plus yi. Okay, I'll let you sort of read these steps, but we're just doing some simplifications and then collecting the real parts and the imaginary part. Pause the video, get a pen and paper out, and just check that that verifies, but I can assure you it does. So this is the real part, because remember, even though yi is the imaginary part, the coefficient of I is real. So all of this is real, and this coefficient of I is also real. So we can say that the real part of the complex quadratic f of z is 2x squared minus 2y squared minus x plus 1. And the imaginary part of the complex quadratic is 4xy minus y. Okay, and to really get a feel for what's going on here, I just wanted to pick some numbers. So now let's just pick values, just why not? Just like you would pick values if you wanted to test where a point is on a regular parabola or quadratic. Let's do that in complex land. So let's say that x is 1 and y is 1. So we're going to get this. Okay, we know that the real part evaluates to this, so we just substitute 1 in, and that turns out to be 0. Okay, so again, just all I did there, take 1. We're just picking this random. These numbers are randomly picked just for illustration purposes. The real part turns out to be 0 if x is 1, and the imaginary part turns out to be 3. So if you substitute x being 1 and y being 1 into the imaginary part here, then you'll get that it's equal to 3. And so what we can say is, if we sort of think about those inputs representing a complex number, so we're saying f of 1 plus I, right? The complex number is 1 because it has a real component of 1 and an imaginary component of 1. So that would represent the complex number 1 plus I. And so it would turn out that you would have the real part being 0 and the imaginary part being 3. So we say thus f of 1 plus I is 0 plus 3i. Okay, and so we're starting to get a feel now because we've got sort of 3 things going on here. We've got an x input, a y input, and then we've got the function evaluated. In this case, it turns out to be 3i. So what we're going to do is we're actually going to come over here and let me explain. We're going to sort of visualize this in 3-dimensional space. Now remember, 3-dimensional space just has an x coordinate, a y coordinate, and a z coordinate. And what we're going to say in order to visualize this, if we just ignore the other stuff for now, just look here, we say the x coordinate is the real part of the complex number. So that's this red axis is the real part. The y coordinate is the imaginary part of the complex number. And z is the modulus of f of z. And the reason we're going to make our last coordinate equal to the modulus of f of z is because when that surface that we create goes to 0, then those points will represent solutions to the complex quadratic in sort of three-dimensional space, which is what we've got going on here. And we'll talk more about this in a moment. But just remember that this complex quadratic f of z, the modulus of that is basically the length from the origin to that complex number, and that's just using Pythagoras, right? We take the square root of the real part of f of z squared plus the imaginary part of f of z squared. So just recalling from before, in our example, it turns out that f of 1 plus I was 0 plus 3i, right? So working out the modulus of that is just 3. Now, this is why it's important to understand what we mean by modulus. But remember, if you think about your Argand diagram, 3i is just sort of on the imaginary axis at 3, and you just need to know the length to get there, right? So that's just going to be, the real part is 0, so it's going to be the square root of 0 squared plus 3 squared. 3 squared is 9, the square root of 9 is 3. So that should make sense. Again, on your Argand diagram, you're just at a distance of 3 from the origin, right? So putting all that together, we can think about this surface that we've got going on here, which is sort of in blue. And let's just think about this point to see where it comes from. So the x coordinate is 1. So that's the real part of the the real part of the complex number that gets inputted. And that's sort of at the x value of 1. We also said that the y value, the imaginary part of the complex number, is at 1. And finally, just in this example, it turns out that the modulus of f of z is at 3 in this case. So that point there, which you can see in red, this point here, has the coordinates 1, 1, 3. Okay, and now if we just move that, because it'll stuff things up, but you can see that this modulus surface, we can call it, just basically maps all those points for all the inputs. Remember, let me just explain. Let me get this the right way around. So for some input, let's get this, something like that. So we've got positive x here, positive y here. So what we're saying is, for some x input, which is the real part of the complex number, and for some y input, which is the imaginary part of the complex number, and the third value outputs the modulus of f of z. And so that's just mapping all of those values, right? So, if you picked x being 1/2, you would end up at some other point on this surface. So this is the modulus surface, which represents the complex quadratic, or the modulus of the complex quadratic. Okay, anyway, so as I said here, as we've already explained, it follows that 1, 1, 3 is a coordinate on this modulus surface. And so bringing it all together, if we go back over here, all the way back to here, our solution to this complex quadratic was 1 plus or minus the square root of 7i on 4. So it follows that on the modulus surface, that corresponds to these points here. These are zeros of the modulus. See how they're on the modulus is 0 at those points? And so those points must correspond to a real value of 1/4, an imaginary component of root 7 on 4, and obviously the modulus goes to 0. So these 2 points represent the real and imaginary parts that are solutions to f of z equaling 0. And there's an error here, let me fix it. All right, hopefully you picked up my error there. It should be 1/4 root 7 on 4, 0, and 1/4 negative root 7 on 4, 0. And they represent the real and imaginary parts that are solutions to f of z equaling 0. And because we get a plus or minus component from over here, right? Plus or minus root 7i on 4. So remember, the x coordinate is the real input, the y coordinate is the imaginary input. And then you get this cool modulus looking surface thing. So I don't know, this isn't part of the specialist course explicitly, but if you want to know sort of what's going on visually when you find a solution to a complex quadratic, I think that's hopefully a useful way to sort of picture things. But for the most part, you'll just do it algebraically. But you know me, I like to have a picture of what's going on. So hopefully you found that useful. If you did, give us a thumbs up. Let me know how you're getting on with the course. If you need any private tutoring, let me know. And I'll talk to you soon. Good luck.